So let us see the works examples for the content what we covered. So we are going to go through what is called stoichiometry work examples now. So the first example what we want to cover is so the problem and the solution is given here. I'll just try to explain this. So ethanol C2H5OH is burnt in a furnace with an equivalence ratio of 1.1. Okay, so it's rich. The reactant mixture is a rich mixture where less air is supplied. Okay, the condition given is if no hydrogen or oxygen is found in the exhaust, determine the product composition per kilomole of fuel. Okay, so that is the problem. So we have given here. See, the ethanol reaction is given here in this. So ethanol C2H5OH. When you write the stoichiometric reaction, so you know that you have to assume a complete combustion. So all the H is converted into H2O. So there are 6 H atoms. So 3 H2O is formed, and C2 is converted into 2 CO2. Okay, so this is the stoichiometric reaction, and but the given data is the equivalence ratio is 1.1. That means you are not supplying the stoichiometric air. The air supplied is 3 by 1.1. So this is actually 3 by phi. Okay, so that is the amount of air which is supplied. So you can see that if phi is less than 1, you will supply more air than the stoichiometric quantity. Now in this case, since phi is 1.1, that is greater than 1, so phi greater than 1, then you get fuel rich mixture. Okay, so now for this the condition given is there is no hydrogen left. This is correct because obviously what happens is hydrogen is a very fast reactive fuel. So what happens is it first consumes all the oxygen. Then remaining oxygen is actually available for oxidizing the C. Okay, so that means that there will be no oxygen left also. Okay, so if the engine exhaust has no hydrogen or oxygen left, so what you should write is here you will form all the H2O. So for example, in stoichiometric condition, you see that for 1 mole of ethanol, 3 moles of H2O are formed. Similarly, in this rich combustion also, first hydrogen is fully consumed like oxygen, like it takes all the oxygen required for its oxidation. So 3 moles of H2O is formed first, but now you can see that for C to oxidize, oxygen is not enough. So what happens is some amount of CO2 is formed and some amount of CO is formed. Correct, because the oxygen is not available. See, 3 moles of oxygen is required for combustion, but you are supplying 3 by 1.1, that is less than 3 for the actual mixture. So you will get some amount of carbon monoxide in the mixture. Okay, so by doing this, say now you have equations for in terms of atom balance. To take hydrogen balance doesn't appear here because it's already balanced, but to take carbon balance, 2 carbon atom in the left hand side, A plus B is the carbon or the carbon atom in the right hand side. So just add them. So you get one equation involving A and B. Similarly, do O balance. In the left hand side, you will see that the fuel has half O molecule, that is half of the O molecule here, plus 3 divided by 1.11 in the oxidizer. So left hand side you have half plus 3 by 1.1 kilomoles of oxygen. Right hand side 3 H2O has 3 by 2 O2. So 3 by 2 O2 corresponding to H2O. Then ACO2 will have A moles of oxygen, and BCO will have B by 2 O2. Okay. So now if you balance this, and you will get another equation involving A and B. So solving these two together, you will get A equal to 1.4546 and B equal to 0.5454. So what is asked is the product composition per kilomole of fuel. So, you have already written the equation for 1 kilomole of fuel here. So, the products formed are 3 times H2O, then 1.4546 times CO2 plus 0.5454 times CO and 10.2545 times N2. So, these are the number of kilomoles of products which are formed. Okay. So, please understand here that if there is a rich combustion and some conditions are given, like in general practice we can take that all the hydrogen is consumed, but let us take example. For example, if this equilibrium ratio is more than 1.1, say it is 1.5 and all, then what happens is even hydrogen may not have enough oxygen to combust. So, in that case you will see our hydrogen remaining in the product. So, for example, H2 will be there. So, you have to include that also, but in this case since the exhaust is measured and it has no hydrogen or oxygen, so you can write like this. Okay. Now, the point when I say no hydrogen is given, I understand that all the hydrogen is consumed. Okay. So, it is formed to, it transformed to water vapor. But what is the point in writing no oxygen? Because already it is oxygen starved, correct? So, you do not have enough oxygen here. So, obviously there should be no oxygen coming out of the exhaust. But the point why we have given here no oxygen is because you can understand that if temperatures are high enough, then products can dissociate. For example, CO2 can dissociate to form CO and O2. So, that dissociation product O2 can come out, but in this case the temperatures are not so high. When the combustion takes place within the furnace, the temperatures are not so high maybe. So, what happens is there is no oxygen available due to dissociation. There is no oxygen available for complete combustion of carbon, as well as there is no oxygen available due to dissociation. So, that is the problem. So, this is the problem where you try to do the stoichiometric analysis of a rich mixture of ethanol and air. Okay. The second problem, in a combustion process with decane, that is decane is straight chain alkane C10 H22 CN H2N plus 2. So, C10 H22 and air is the oxidizer, and when it is burnt, the products are analyzed using an volumetric analyzer. Okay. So, for example, ORSET analyzer is a typical example for a volumetric analyzer which measures the product composition. Okay, this ORSET analyzer, normally when you let in the exhaust gas into this ORSET analyzer, first of all you filter out the water vapor. So, condense the water and filter out the liquid water, then the other gases are fed. So, that means you are measuring only the dry mole fractions. Okay. So, such an analysis presents 83.61 percentage of nitrogen, then 4.91 percentage of O2 and 10.56 percentage of CO2, and you can see that there is another some quantity of CO also. So, here O2 is also present and CO is also present. Okay. So, that is what I told in the previous problem, that O2 may be there. So, obviously this may be a problem where O2 oxygen is supplied in excess, like than required for the complete combustion. However, due to some dissociation, CO is formed. Okay. So, now for this scenario, so you do not know anything else, it is a dry product, we do not even know the mole percentage. See, we know that product mole fractions are given because the volumetric fractions are nothing but mole fractions. So, you know the mole fractions in this dry basis, like there is no water vapor involved, but obviously you know that when an hydrocarbon burns, you will produce water vapor. Okay, but the water vapor has been condensed and the liquid is removed. So, other gases are the composition of other gases are presented in this list. Okay, now what we require to find is the equivalence ratio, then percent theoretical air of the reactants, and the molecular weight of products, mole fraction of CO2. These are we want. Okay. So, now if you add up this dry fractions, see for example 83.61 nitrogen plus 4.91 oxygen plus 10.56 CO2 and 0.92 CO, you will see that 100 kilomoles or 100 percentage. So let us assume that 100 kilomoles of dry products are formed. Okay. In 100 kilomoles of dry products, we have 83.6 kilomoles of nitrogen, 4.91 kilomoles of oxygen, 10.56 kilomoles of CO2 and 0.92 kilomole of CO. So let us assume that these are the products. I will now like what I am trying to do here is change the percentage into kilomoles. So to obtain this much kilomoles of dry products excluding the water which is formed, how much fuel I have to burn? Let us assume that I burn x kilomoles of fuel. You can also assume some kgs. Okay, so here I am assuming x kilomoles of decane is burnt to produce 100 kilomoles of dry products as given in the problem. Okay, so if I do that, then I can write the equation, chemical equation as x moles of C10H2 here, C10H22 plus I do not know how much amount of oxidizer is required or number of moles of oxygen. So A times the air is CO2 plus 3.76 N2 giving, I do not know again the number of moles of H2O from, because this is only dry based, on dry base only I have got the other product composition. So let us assume B kilomoles of H2O is formed along with whatever is given here. So CO2 10.56 kilomoles of CO2, then 0.92 kilomoles of CO and 4.91 kilomoles of O2 and 83.61 kilomoles of N2. So these are all the dry products. So the percentage is converted into this. So to achieve this dry products composition in terms of kilomole, I have to burn x kilomoles of fuel and with A kilomoles of A into 4.76 kilomoles of air, and in this way B kilomoles of H2O is formed. But I can see that straight away I cannot get the value of B because 22x equal to B. So first I have to get the value of x. So now let us do the atom balances for this equation. So by n balance, straight away you can see that A into 3.76 will give you the n 83.61. So you will get directly the value of A. So that is the amount of oxidizer supplied. So number of kilomoles of air is 22.2367 into 4.76 kilomoles of air is supplied. Now do the C balance because you know CO and the CO2's number of moles in the products are known. So 10x in the left hand side will be equal to 10.56 plus 0.92. So you will get the value of x. So that means instead of just burning 1 kilomole of fuel, I am burning 1.148, approximately 1.15 kilomoles of decane. So the fuel is slightly higher than 1 kilomole, so it is 1.15. Then now do the H balance to get the value of B, that is 22 into x. Now value of x is known, so 22 into 1.148 will be equal to, in the right hand side, 2 times B, the number of H atoms. So B will be equal to 12.628. So the unknowns are x, A and B, we have got that. Okay. Now what we try to do is, we will try to write the equation. You did not even do that, but I am trying to do this. See, for example, normally it is our practice that you can see this in the previous example also. It is our practice to write the equation here in 1 kilomole of fuel, correct? So taking 1 kilomole of fuel, we are writing the equation. But in this case, we have taken x kilomoles of fuel. So now try to divide this by x. So you get the equation. Okay. Now after evaluating x, A and B, which are unknowns, we are trying to write the equation in terms of 1 kilomole of fuel. So now dividing throughout by x, I am writing this equation like this. Now see, the number of kilomoles of oxygen is 19.37. So you find the actual air fuel ratio, which is nothing but 19.37 times 4.76, number of moles in the air, 1 plus 3.76 into molecular weight of air. So this is the number of moles of oxidizer into this is the number of moles of air, then this is the molecular weight of air. Okay. So now divided by the molecular weight of fuel, which is 10 times 12 plus 22. So 120 plus 22, this is the molecular weight of molecular weight of C10H22. Okay. Okay. So now it will be 18.726. So obviously we know that approximately 15 kilogram of air is required to burn 1 kg of hydrocarbons like C10H22. So actually the actual stoichiometric air fuel ratio is, so you know A is x plus y by 4. So x equal to 10, y equal to 22. So A will be x plus y by 4 into 4.76 into 28.84 by 142. This will be stoichiometric air fuel ratio, you get around 15. But you are supplying more than this. So the equivalent ratio is less than 1 because you are supplying, the actual air supplied is higher than the stoichiometric air. So stoichiometric air fuel ratio, this is stoichiometric air fuel ratio divided by actual air fuel ratio. Okay. So that is the ratio, equivalence ratio, definition of equivalence ratio. You will get 0.8. So you are supplying excess air. Even if you supply excess air, due to dissociation, you find that CO is formed in the, a small amount, a little amount of CO is formed in the products because of dissociation. Okay. So now what is asked? So the equivalence ratio is got, then percent theoretical air, percentage theoretical air is 100 by 5, so 100 by 0.8, so 125%. Then you want the molecular weight of the products and the mole fraction of CO2. Okay. So total number of moles you can find here. Total number of moles is, just add this 11 plus 9.1986 plus 0.801 plus 72.83 plus 4.277, that is 98.81 kilomoles, actually kilomole. And mole fraction of CO2 is number of moles of CO2, that is 9.1986 divided by 98.1, that will be this. Okay. Similarly, you can do the molecular weight of the products. It is nothing but sigma xi, that is mole fraction of each product species, multiply it by its own molecular weight. So xi mi. So now we can write this as ni, you know this. So ni is 11, 9, etc. into mi divided by n total. So you will get the molecular weight is this. This is very close to nitrogens because nitrogen's number of moles are very high. Mole fraction is very high for nitrogen. Okay. So you can see that in this case, by just knowing the dry composition of the products, we can find the amount of air supplied. Okay. So the amount of air supply can be got, and so the product analysis is very important. Okay. So by this product analysis we are able to get the this. So you can also determine how much water vapor is formed by this. So once you know the fuel composition, we can find how much air has been supplied to get this product and so on. It is a simple stoichiometric calculation. Okay. So this is the way you do this. Okay. So so let us see the work example 3. Now we will consider a fuel mixture, okay, which consists of by volume 10% CO, 40% H2, 35% CH4, 4% C2H2, and some oxygen, 2% of oxygen and nitrogen and CO2 are also present. Okay. Now what is required is, we have to find the stoichiometric air fuel ratio and product composition when this fuel mixture is burnt with 20% of excess air. Okay. So that is the requirement. So now let us consider 1 kilomole of fuel as per the volumetric analysis. So the mole fractions which is given here, actually the volumetric fractions are mole fractions. So we will just divide it by 100, so that you will get mole fractions. When you add it, it will be 1. So 1 kilomole of fuel mixture we will take, which consists of say 10 by 100 0.1 CO, then 45 by 100 0.45 H2, then 35 by 100 0.35 CH4, then 4% C2H2 0.04 C2H2, then 2% oxygen, nitrogen and CO. So 0.02 times these 3. Now oxygen, we do not know how much moles of oxygen to be added. So let us say A moles of oxygen is added to form B moles of H2, C moles of CO2 due to combustion plus already 0.02 kilomoles of CO2 is present in the reactant mixture. So that will also translate here. So C plus 0.02 CO2. Similarly, nitrogen, the oxygen stream is 3.76 times A plus what is present in the fuel stream is 0.02 N2, so 0.02. So that will add up. Okay. Now the oxygen in the fuel and the oxygen in the oxygen stream both will be used to completely burn the fuel components in the fuel mixture. Okay. So like we did for ethanol, the O in the ethanol was utilized for burning, complete combustion. So we supplied only lesser air. Similarly, since fuel itself has some inherent air, we supply only air excluding excluding that part. Okay. So here, so this will be the fuel mixture. Okay. Now do the C balance 0.1 CO, so 0.1 here, then 0.35, then 0.04 into 2, that is 0.08 in the left hand side, plus CO2 has 0.02, so that is the carbon balance. Right hand side you have C plus 0.02. So solving which you get C equal to 0.53. Now H balance, H2 is say 0.45 here. So I am writing 0.45, then CH4, so 4 CH4 is there, so 0.35 into 2 is 0.7 plus here C2H2, so that H2 is there, so 0.04 here. Left hand side these are the H2s and the right hand side B. So solving which you get B as 1.19. Similarly, O balance is 0.1 into O2. 0.1 divided by 2 times O2 plus here 0.02 O2, so 0.02 give plus A O2 in the left hand side, reactant side, product side B by 2 O2 for the hydrogen, then C plus 0.02 O2 here. Okay, that is all. So now if you solve for, so you know B value and C value from the C and H balances, so calculate A. So that will be the stoichiometric reaction. 0.1 CO plus 0.45 H2 plus 0.35 CH4 plus 0.04 C2H2 plus 0.02 O2 plus N2 plus CO2 plus oxidizer 1.075 O2 plus 3.76 N2 gives products 1.19 times water vapor, 0.55 times carbon dioxide and 4.062 times nitrogen. Okay, so this is the stoichiometric equation. Okay, so the continuing the example for the fuel mixture, you can see that the amount of oxidizer required is 1.015 and these are the composition of the products which have been measured basically. Please understand the stoichiometric reaction, you do not have any oxygen left over in the fuel, so that is the way you write this. So now the molecular weight of fuel is calculated because the mole fractions are known. We can calculate the molecular weight of the fuel mixture and you can see that is 12.42. So here this 104 is nothing but 32 plus 28 plus 44, which are these three. Okay. So now you do this and the molecular weight is very low, kg per kilomole, because you can see that the 40% of hydrogen and 30% of methane which have lower molecular weight, these compounds are present. So the overall molecular weight has reduced to 12.42. Now stoichiometric air fuel ratio is 1.075 into 4.76 into 28.84 divided by 12.42. So that will be 11.882 kilogram per kilogram of fuel. Okay. Now what is asked is when it is, so this is the stoichiometric air fuel ratio, that is the first one what we have to determine. Second one is when the fuel mixture is burnt in 20% excess air. So how will you do the same fuel mixture plus 1.07 times into 1.2, so 20% excess air. You see that there is some oxygen present in the product. So the complete combustion again, like in stoichiometry, complete combustion takes place. So the number of moles of H2O is 1.19, number of moles of CO2 is 0.55 and N2. So this will be the composition of the product. So we want composition of the products when 1 kilomole of fuel mixture is burnt. So that is this. So this is the composition of products. Okay. Okay. Now let us consider a problem where methanol is used and it is evaporated through a porous wick. Okay. So in an atmospheric pressure pre-vaporizer, a horizontal porous wick saturated with methanol is kept in flush with the bottom wall of a horizontal wind tunnel. So we have a horizontal wind tunnel, and in which horizontal porous wick. So this is the porous wick, horizontal porous wick. So this is kept in flush with the bottom. This is the bottom. So this is wind tunnel. So bottom wall of the wind tunnel, this porous block is kept in flush. Air flows at a given velocity over the surface. So air comes here like this and flows over this surface of the wick, and so it has some velocity, and temperature is 320 Kelvin. So that is kept constant, and the velocity is varied, and it is actually supplied like this. Okay, now as a result, so because this is at 320 Kelvin higher temperature than the ambient, so methanol vaporizes. And please understand that this wick is saturated with methanol. So always methanol is supplied to this, so that this wick is always saturated with methanol. So as the methanol vaporizes, more and more liquid methanol will come and saturate to the wick. So that is the problem. So it is a steady evaporation problem, where when you vary the U, you will get more evaporation and so on. So air flows at a given velocity over the surface of the wick at a temperature of 320 Kelvin. As a result, methanol vaporizes and mixes with air. So here we get methanol vapor plus air. So pre-mix methanol vapor and air. So this is called pre-vaporizer. So I try to vaporize the fuel and pre-mix it with air and send it to the combustion chamber. So maybe combustion chamber is next to the wind tunnel. Okay, now so reactor mixture flows out of the wind tunnel into the combustion chamber. The cross section of the wind tunnel is 0.1 meter by 0.1 meter. So the cross section of the wind tunnel is, so area of cross section is 0.1 by 0.1 meter square, and surface area of the porous plate, this surface area of the porous plate, so AP will be 0.05 meter square. Okay, now at an air velocity of 0.5 meter per second. So when u equal to 0.5 meter per second, the evaporation rate per unit area of the porous plate, okay, the fluid is evaporating from this, the evaporation rate per unit area is, so we will say mass evaporation rate, okay, per unit area of methanol fuel is 0.017 kg per meter square second. Okay, now when the air velocity is increased to 2.5 meter per second, so when u equal to 2.5 meter per second, the evaporation rate increases to 0.027 kg per meter square second. So that is the evaporation rate of the fuel is now 0.027 kg per meter square second. Okay, so kg per second per meter square, that is the evaporative flux. Okay, now determine the equivalence ratio of the reactant mixtures at these velocities. So now the evaporation takes place, and what is the equivalence ratio of the mixture? Methanol vapor and air comes out of the wind tunnel and goes into the combustion chamber. What is the equivalence ratio at these two velocities, 0.5 meter per second or 2.5 meter per second? So this is the problem.